So we've previously looked at the factor theorem, where if we substitute a number into a function, if we get a value of 0, then we can determine that we've found a factor of that function. So today we're going to look at the same idea, except we're going to look at something called the remainder theorem. So if we take this function here, f of x, and we substitute in the value for 3. So we were doing the same thing when we were looking for factors. We were substituting values in and determining what the output was. And we were looking for ones that had 0. So let's see what happens when we substitute 3 in here. So considering the output, it's 27 times 2, which is 54. Take away 9 times 4, which is 36. Plus 21. Take away 37. So in this example, we're going to get, instead of 0, we're going to get a remainder of 2. Right? So previously we would have discounted this solution and we would have said that x minus 3 is therefore not a factor of f of x. However, we can use this to our advantage. So let's consider the same thing when we do long division. So if we had to divide 2x cubed minus 4x squared plus 7x minus 37, and we divided by, well, we're dividing it by x minus 3. And we want to consider what comes out. Okay, so we'll do the same thing as before. How many times can x go into 2x cubed? And the answer would be 2x squared. And we'll multiply through. So we need to multiply into both numbers, and we would get 2x cubed. And we would get minus 6x squared. Okay, and then we would subtract. And we have minus 4x squared minus 6x squared, so that's going to become positive. So we'll get plus 2x squared, bring down 7x. How many times does x go into 2x squared? And the answer would be 2x. Multiply through, we'll get 2x squared plus minus 6x, and we will now subtract. Again, remembering that this is subtraction, so it's minus minus, so we will get minus 6x, or minus 6x, which is positive, so we'll get plus 13x, bring down the negative 37, and this will be plus 13, multiplying through 13 times minus 3 is minus 39. Once again, we are subtracting, so minus minus is a positive, so we will get a remainder of 2 over here. So just like you would have if you'd done long division on a normal problem, you've got a remainder. Here we get a remainder. Okay. So the important coincidence we want to note here is that when we substituted 3 into the function, we got a remainder of 2. And likewise, when we divided by the factor x minus 3, we got another polynomial, and we also got a remainder of 2. So the important takeaway here is that we could algebraically write that 2x cubed minus 4x squared plus 7x minus 37 is equal to, right, these two factors, well, x minus 3, sorry, it's not a factor, this dividend or divisor, and this is the quotient that we got out the other side, and there was a remainder of 2. Okay, so in general, what we can say is, if you take a polynomial and you divide it and get a quotient, right? It's the same as saying that polynomial can be written as the divisor multiplied by the quotient plus whatever remainder stays in place. And we saw that if we got a remainder of 0, that this divisor was then also a factor. Okay. So let's say if we have a polynomial p of x and we divide it by some linear factor to give us another polynomial and a remainder, okay, then how we would write that algebraically is if we have p of x, right, we can write that as x minus c times q of x plus r. Okay, so we divide the polynomial by some linear factor and we get a quotient, okay, plus a remainder. Okay, so we know that this divisor is not a factor. Okay, now if you see, if we substitute in c into our equation, x is going to replace with c, and we're going to have the remainder at the end. Now this over here is going to become 0, which means this is going to become 0. And we can say that if we substitute it in f of c, we will be left with the remainder. Okay, and that's what we noted when we substituted the value of 3 in the first time. Okay, we got the same value when we substituted the value of 3 in, when we divided the polynomial by what we would normally have considered a factor of x minus 3. Okay, so this then gives rise to what we call the remainder theorem. So just like the factor theorem, the remainder theorem states that if p of x is a polynomial is divided by some factor, some linear factor, x minus c, then the remainder will be whatever we substitute, as if we substituted c into the function in the first place. Okay, and this can be further expanded to if p of x is divided by ax minus b, for instance, okay, then the remainder will be just like with the factor theorem, as if we were substituting in a or b over a. So let's look at some examples of how we can use the remainder theorem. So here we are asked to find the remainder when this function is divided by x plus 3, and we can do this two ways, either algebraically or using, algebraic division or the factor theorem. So using algebraic division, we can consider, well, how many times does x go into 7x cubed? And that would be 7x squared. And as before, we just multiply throughout. So we'll get 7x cubed plus 21x squared. Subtraction next. So 6 minus 21x. So we're going to get minus 15x squared. And we're going to bring down minus 40x. So how many times does x go into minus 15x squared? And that will be minus 15x. Multiply through. 15 times 3 is minus 45x. Subtraction next. So keeping track of our double negatives. So we have 40 minus minus, which is positive. So we're going to get 5x. Bring down 17, repeat, how many times does it go into 5x? It's 5 times, multiply out, and we end up with a remainder of 2. Okay, another way we can find the remainder is by using the factor theorem, right? Remember, the factor and remainder theorem are actually the same. if we substitute a value into the or a factor into a polynomial, we will get the remainder, and usually if the remainder is 0, then we know it's actually a factor. So first of all, let's say that this polynomial is called f of x. And let's substitute in the value. Well, we want to divide by x plus 3, so the value we have to substitute in is, like with the factor theorem, is going to be minus 3. Okay, and very quickly we will have 7 times minus 27, so that's going to be minus 189 plus 54 plus 120 plus 17, and this will be equal to 2. And so, as before, both methods would present us with what the remainder is. Okay, so the factor theorem tells you what the remainder is, and if you use algebraic division, you can get obviously what the quotient is and what the remainder is. Okay, so depending on what the question might ask you, these are the two methods that you could consider using. All right, so if you are only considering what the remainder was, we can see the factor theorem is much faster, but if we needed to know what this other polynomial was, then obviously algebraic division will be the better solution. Okay, let's take a look at a more complex problem with the remainder theorem. So in this example, we're like with the factor theorem, we're going to be given certain things or certain factors that a polynomial can be divided by, and in this instance we're given using that we're asked to solve for the values of a and b. So the values of a and b are constants in the polynomial, and as with any question where you're asked to solve for two unknowns, the most logical scenario is that we're looking to make two simultaneous equations, okay? And we're given two pieces of information in order to create those simultaneous equations. So using the remainder theorem, we know that if we substitute in, or if we divide the polynomial by x minus 1, we'll get a remainder of 1. That means if we substitute in 1 into our equation, we should get a value of 1. And expanding that out, we can say that, well, if we substituted in the value of 1, so we'll get 2 times 1 cubed plus a times 1 squared minus 9 times 1 plus b. This should be equal to the remainder, which is 1. And we can just simplify this as 2 plus a minus 9 plus b equal to 1. And we can move all the numbers over to the other side, and we can get a plus b is equal to 8. So there's our first simultaneous equation. In exactly the same sense, we can create the second simultaneous equation by saying if it's divided by x plus 2, we get a remainder of 19. So if we substitute the value of minus 2 in, we should get 19. Expanding that out, we can say 2 times minus 2 cubed plus a times minus 2 squared minus 9 times minus 2 plus b. That must be equal to 19. So this will give us minus 16 plus 4a minus, well, it would become plus 18 plus b equal to 19. And that leaves us with 4a plus b equal to 17. And there's our second equation. If we look at the two equations, we've got a single b in both equations, so we can take one minus the other. So I'm going to take equation 2 and subtract equation 1. So I'm going to get 4a plus b equal to 17 minus a plus b equal to 8. Remembering we're subtracting, so we're going to get 3a plus 0 equal to 9, so A is equal to 3. And we've got an equation for B. We can say that A plus B is equal to 8. A is equal to 3, so 3 plus B is equal to 8. So B is equal to 5.